Let's take a look at this problem number 3. These problems are gradually going to get a little bit tougher. The notation fg, this is just the name of a new function, but it's telling us how this function was built, how it was created. It was created by multiplying the function f with the function g. If we write f as a fraction, x squared minus 9 over 1 times x over x minus 9. So when we multiply fractions together, we multiply straight across in the numerator, straight across in the denominator. I'm going to put the x in front of this radical. And that's as far as we can simplify it. We can't simplify that any further. So there is our new function, fg, that we built by multiplying f and g together. So that is our final answer for part A. In part B, they want us to create a new function through division, to take f of x and divide it by g of x. F of x is this radical. G of x is a fraction. So we have a fraction within a fraction, which is generally referred to as a complex number. We want to simplify this. Division is the same thing as multiplying by the reciprocal. So we have our numerator, and instead of dividing it by this divisor, we change the division to multiplication. If we take the reciprocal of the divisor, if we make this over 1, then we can multiply these two fractions together by simply multiplying across in the numerator and multiplying across in the denominator. This x minus 9, I'll write that binomial out in front. Now, it is the entire thing. I do need parentheses around it. It's not 9 times that, it's x minus 9 times this radical. So the parentheses are important. All of that is being divided by x. This is a term, so I can't cancel those x's. That's algebraically, that would be incorrect. So this is my final answer. F over g of x. So there's our answer for part B. For part C, it's a division again. At this time, the g of x is in the numerator, f of x is in the denominator, g of x is this fraction. So since the numerator is a fraction, this is a complex fraction. I'll make my divisor a fraction by just putting it over 1. Division is the same thing as multiplying by the reciprocal. So I've got my numerator, and instead of dividing by this fraction, we'll multiply by the reciprocal of that fraction. When we multiply fractions together, we simply multiply the numerators and multiply the denominators. Now, there may be some students that recall that we are not supposed to have radicals in the denominator. And if this were a section where that was the emphasis that was being taught, I think that rule really came about in the days before technology, when you had square roots and logarithms and trigonometric functions that all used tables. You went and looked things up, and some of the properties with logarithms and stuff, I just think to make that lookup in the tables easier, they rationalized denominators. At least that's the only thing I can think of as to why they always had that rule. Well, today, with computers and technology and handheld calculators, the need for the tables has gone away. But even in my lifetime, when I was in high school, I did purchase a CRC handbook of chemistry and physics, and the main reason that I purchased that was for the tables, because for most of my high school, I didn't have the calculator that I did have are just the dollar type calculators that you can pick up at the Dollar General or something, just those white iStep calculators. I didn't have a calculator that had a lot of different features and stuff on it until late in my senior year of high school. Alright, so if we were to rationalize the denominator, it's not really that awful. If we were to multiply by the number 1, but if we were to write 1 as x squared minus 9, what would we get? Well, I've said this now several times in the videos, to multiply fractions together, you just multiply straight across. So in the numerator, and in the denominator, when you have a radical times itself, the radical goes away. X squared minus 9 does factor to x plus 3 and x minus 3, but nothing reduces. So you may see people, we may leave our final answer like this, or if we rationalize the denominator, we'll get an answer like that. The domain of each of these, to find the domain, the first one in part A was the product. I don't necessarily need to come back and look at that expression. I can use the domain of f and the domain of g to determine what the domain of that product is. So to find the domain of f, we look underneath the radical, and x squared minus 9 is greater than or equal to 0. And I did put another Edpuzzle video on here of someone else. Can't remember if it was from patrickjmt.com or if it was from Professor Rob Bob on YouTube, that was solving quadratic inequalities. Here with quadratic inequalities, we always want to get 0 on one side, and then on the other side, let's factor it. And that divides the number line into different regions, and these boundaries of these regions are typically called critical points. -3 and +3 gives us a 0, and 3 minus 3 gives us a 0. Since this is not a strict inequality, since it says greater than or equal to, when we look at our boundaries, we shade them in. And like I say, that's because of this underline, because of equality. that splits my number line up into 3 regions that I can give them any name, so I just call them A, B, and C. I want to come in and pick a test point from each region and plug it into my inequality to determine whether that inequality is a true statement or a false statement. If it's true, then it's going to be true for every number in the region, and I shade the whole thing. If it's false, it'll be false for the entire region, and I cross it out. So let's pick -4 to be a test point in region A. And whenever you're between a negative value to positive value, 0 is always a fantastic test point, unless it is itself a critical point. We don't want to pick the critical points to plug them back in. We already know that they're going to be included. And let's over here in region C, let's pick x equals 4. So when x equals -4, what do we have with this inequality? We've got -4 plus 3, which is a negative number, and -4 minus 3, which is a negative number. And a negative number times a negative number is positive, so that means that this is a true statement, and that we would shade in all of these values. Maybe I should use it black because my endpoint there was black. So all of these are shaded. If we pick 0, then we have 3 times a -3, and that is a false statement. -9 is not greater than or equal to 0. So since that is false, we do not shade in any point in that region B. If we pick +4 and plug it in, then 4 plus 3 is positive, and 4 minus 3 is positive. And it's true that a positive number is greater than or equal to 0. So, in interval notation, how do we describe this number line? The domain for f is from -infinity to -3 union +3 to infinity. Now, that is not my final answer. It said the domain of each of these. Well, that isn't even, it gave us f, but I'm going to use that to find the domain of the product fg and the domain of the division f over g and g over f. Now, let's come in and find the domain for g. It's a little bit easier. We can look by inspection. There is no radical. There is a variable in the denominator, and 9 minus 9 causes division by 0, so we want to throw out the number 9. So from -infinity to 9 union 9 to +infinity. So let's erase this to give ourselves some room. We want to find the domain for part A was f times g, which is going to be the intersection of the domain of f intersected with the domain of g. And if you have a hard time visualizing what numbers are in both sets, then draw 3 number lines. In the first number line, and let's include all of the boundary numbers, -3, +3, and 9. In the domain of f, -3 and +3 are shaded, and to the left of -3 is shaded, and to the right of +3 is shaded. If we look at the domain for G, 9 is not shaded, but all of the numbers to the left of 9 are, and all of the numbers to the right of 9 are. So to be in our intersection, you have to be shaded in both sets. So let's start with these boundaries. Is -3 shaded in both? It is. So it's shaded in the intersection because -3 is in this set and it's also in this set. See, the word and is different than the word or. 3, oh, I forgot to mark -3 and +3. There, that's just for a visual aid. I mean, we knew it was there. So 3 is shaded in both sets, so it's shaded here. Now 9 is shaded in the domain of F, but 9 is not shaded in the domain of G, so it is not shaded in the domain of FG. So are all the numbers to the left of -3 shaded in both? Yes. So they'll be shaded in the domain of FG. The numbers in between -3 and +3, are they shaded in both? No, so they won't be shaded in the intersection. What about between 3 and 9? That's shaded and that's shaded. So it's shaded here. What about values that are greater than 9? It's shaded here and it's shaded there. So it's shaded in the intersection. So now for the domain of this product FG, this new function that we built, we want to describe this shaded region in blue down here. From -infinity to -3, there's a bracket there, union, because or you're in this interval from 3 to 9, or from 9 to infinity. So this is our first answer in part D. We also want to find the domain of F over G and the domain of G over F. Alright. Now, I'm going to keep that. I'm going to erase this work here. And move our first answer up here. The domain of F over G is, well, it's this domain, the domain of F intersected with the domain of G, but then we have to add any constraints. We're going to add anything that would cause G of X to equal 0. We're going to throw it out from the domain. So we want the values of X that do not cause G of X to be 0. So G of X is this X over X minus 9. If we temporarily set that equal to 0, well, that's saying if X is 0, this fraction reduces to 0. We don't want that to happen. But look at our answer for the domain of FG. 0 is already excluded. So this isn't going to change our answer. Had it excluded the number 4, we'd have to come in and say, well, 4 is between 3 and 9. Or had this been a 10, well, 10 is bigger than 9, and we'd have to come in and throw that value out. But 0 has already been thrown out. So the domain of F over G just happens to be the same answer as our product FG. And that will not always be the case. So here is the domain of our answer from part B. Let's erase this previous work because we still have the domain from part C to do. Now, will it be the same answer as this? Yeah, maybe, but I don't know yet until we look at it. The domain of G over F is the intersection, the domain of G intersected with the domain of F intersected. Well, we have to make sure that f of x is not 0. Okay, so when is f of x equal to 0? Well, x squared minus 9, if we temporarily set it equal to 0 to solve this so we know what to avoid, if we square both sides of this equation, the radical will go away. If we factor the left-hand side, we can see that we want to make sure that -3 and +3 are not in the domain, because if they were in the domain, this denominator would be 0 and we wouldn't get a corresponding y value. So we are going to have to modify that, because currently you can see brackets around the -3 and +3. So we want this answer, but we want to exclude the -3 and +3. So from negative infinity to -3 excluding -3 excluding +3, we also have to exclude 9, because that was part of the exclusion when we intersected at the domains of f and g. So here's our final answer for the domain of C. Alright, so I believe that's all of problem number 3, and I hope that helps.